The goal of this presentation is to identify the technology performance improvements needed to enable a range of future products, services, and interventions that could contribute to the following Sustainable Development Goal. By 2030, substantially reduce the number of deaths and illnesses from outdoor particulate air pollution in Asian cities. To reduce that number, we will focus on reducing the emissions of particulate matter in Asian cities. We were assigned GE as our starting point for this presentation. We therefore looked at GE power in order to identify which applications and technologies are the most relevant in order to reduce Asian air pollution. The first important step was to understand the variety of the industries GE is involved in. As you can observe, the company works in many different areas such as nuclear, solar, and wind power. We decided to focus on coal power for multiple reasons. First of all, according to Forbes, coal is the fastest growing source of energy and it will overtake oil as the world's largest energy source by 2025. We also chose coal as it is widely used in Asia and more particularly China, the country we will be focusing on. Indeed, there are more coal power plants installed in China than there are in the US, the UK, and India combined. Finally, according to the Journal of Environmental Protection, 36.4% of the PM2.5 particles in Beijing come from coal combustion, and in suburban Beijing, coal combustion contributes to 48.6% of the PM2.5 particles. Therefore, a large part of the particulate emissions around Beijing, in China, are due to the coal combustion within coal-fired power plants. Within the coal industry, different applications are possible. However, we focus our attention on the air quality control systems, AQCS, as they directly impact the particulate emissions from coal combustion, but also because it seems to be a very promising area in this industry. Indeed, we looked at the patents in the AQCS area and found that Alstom, a company recently bought by GE, has a significant number of patents, which shows that they have very strong R&D activities related to the AQCS area. Indeed, we know, for instance, that Alstom has one of the largest AQCS laboratory centers worldwide, located in Sweden. Finally, we identified the technologies and sub-technologies within the AQCS application. We will mainly focus on two particulate control sub-technologies: fabric filters, FF, and electrostatic precipitators, ESP. These technologies are therefore the most relevant when dealing with coal power plants in order to reduce Asian air pollution. We can see on this image of a coal-fired power plant all the technology solutions provided by Alstom. We will be focusing on the FF and ESP technologies, which affects the red circle part of the coal-fired power plant. From now on in the presentation, we will explore what the fabric filters and ESP technologies are, how some of their performance characteristics are changing over time, and how these have a limited future in relation to achieving our goal. First, let's go into the details of fabric filters. A fabric filter is an air pollution control device that removes particulate matter out of the gas flow released from combustion for electricity generation. First, we looked deeper into the technology and found out a range of performance characteristics. The key characteristics to analyze are the collection efficiency and the costs. In fact, fabric filters are regarded as being highly efficient thanks to the capacity to collect particles whose size is below 2.5 micron. However, the technology requires high operational and maintenance costs. In parallel, we looked at how fabric filters improved over time. As it can be observed on the timeline, there are three main improvements over time: increasing the length of bags, increasing the amount of bags per pulse valve, and finally, developing improved gas flow and pulse cleaning system design. Such improvements enable to reduce steel weight, capital costs, and environmental footprint. However, the technology is also facing limits today. The main challenge observed with fabric filters is high operation and maintenance costs. Finally, we tried to estimate how the technology will improve in the future. Assuming that the improvements remain similar to the past improvements, the size of the bags would increase to 20 meters, whilst the number of bags per pulse valve would continue to increase too. Such improvements would lead to higher costs. For instance, bag replacement is required every 3 years. The more bags there are, the more expensive the maintenance costs are. Therefore, there will be a point in time, estimated to 2025 here, where the FF technology will reach a breakpoint. The technology will become too costly to be maintained and therefore to be used. Let's look at our second sub-technology, the electrostatic precipitator, ESP. An electrostatic precipitator is a filtration device that removes fine particles such as dust from a gas flow. The particles are charged when passing through high electrostatic fields and consequently move towards the collecting plate. On the right-hand side, we can see the plate precipitators, which are the main factor for extracting the particles from the gas flow. Traditionally, in the power industry across the world, electrostatic precipitators have been the technology used for the removal of particulate matter from coal-fired boilers. Here, you can observe the performance characteristics of ESPs. Following the same logic analysis as for fabric filters, we looked more in depth into collection efficiency and costs. Indeed, ESP is regarded as being a technology cheaper than fabric filters. However, it deals with a lower collection efficiency. Indeed, the main challenge observed with electrostatic precipitators today is to increase collection efficiency. This is mainly due to the fact that ESP collection efficiency is highly dependent on two things. First, it is dependent on the type of fly ash, which depends on particulate size, composition, and resistivity. Then, the ESP collection efficiency is dependent on flue gas properties depending on the gas's temperature and composition. Consequently, these factors make the dust emission hard to be reduced to the current regulations, which are less than 50 milligrams normal meter cube. Previously, the addition of flue gas conditioning systems, as well as the improvement of plant management systems, controllers, and distribution screens, enabled the technology to lower its costs. However, the ESPs are still not as efficient in collecting particles in the range of 0.1 to 1 microgram, which are the main cause of health issues. Hence, ESP is only just able to meet the current emission regulations, which are less than 50 milligrams normal meter cube. In addition, as regulations are predicted to be tightened, ESP technology will struggle to increase its collection efficiency. Therefore, if the ESP technology does not increase its efficiency, it will not be able to meet the future regulatory requirements by 2025. As FF and ESP technologies have a limited future in relation to achieving our goal, we also looked into an alternative technology which is more recent, the electrostatic fabric hybrid particulate collector, EFPC. Is a combination of ESP and FF. We will call this technology the ESP-FF hybrid system in our presentation. The solution involves using ESP sections as the dust precipitator and installing fabric filters in the remaining ESP housing, forming a compact hybrid particulate collector. This new hybrid ESP-FF system aims to become more viable than the individual technology by using the advantages of both technologies. On this table, we compare three common performance characteristics of FF, ESP, and hybrid: capital costs, operational maintenance costs, and collection efficiency. Hybrid has lower capital costs than ESP, but can't beat FF. It also has lower operating and maintenance costs than FF, but can't beat ESP. The collection efficiency of hybrid is higher than only FF and ESP. So overall, hybrid systems have average costs compared to FF and ESP, but its collection efficiency is higher. It therefore seems like hybrid systems is a technology that will be widely used and enable us to reach our goal in the future. However, hybrid technology currently has a performance gap. When the FF section is installed into the ESP to form a hybrid particulate collector, the gas flow distribution in the system becomes non-uniform. This negatively affects the collection efficiency of ESP because it is directly related to the uniformity of the flow distribution. If further R&D is devoted to ensuring uniform flow distribution, near zero emissions from the thermal power plants would be possible. Now, let's look at the future of regulations in Asia, specifically China, so that we realistically see the possible impact of hybrid technologies. China has taken important steps towards reducing emissions from thermal power plants, and we expect the standards to tighten further from the current standard of 20 milligrams per cubic meter to 10 by 2020 and to just 5 by 2030. The current FF technology is able to guarantee under 5 milligrams per cubic meter emissions and thus may meet the future predicted standards. But hybrid technology is able to reach 99.91% collection efficiency, which is higher than the collection efficiency of any removal technology used alone. In 2005, all thermal power plants in China use ESP for PM control. It is important to note that a significant advantage of hybrid technology is that it is feasible and cost-effective to retrofit into power plants currently using ESP. If tighter standards are implemented at the current level of technology, over 30% of thermal power plants are expected to switch to hybrid technology by 2030, as shown by S1. In the S2 scenario, we assume that the current performance gap is eliminated and uniform flow distribution is ensured for the hybrid design. In this scenario, we expect over 50% of thermal power plants to switch to hybrid technology by 2030. Research demonstrated that if hybrid ESP-FF are used by all power plants, PM 2.5 emissions can be reduced from 898.5 to 47.48 thousand tons. Higher usage levels of hybrid technology will certainly contribute to reducing emissions, and if hybrid technology is further improved, the results will be highly favorable for achieving cleaner air in China by 2030.